Hi, I'm Hao Jian, and I'm going to present our project WiSh, a wireless ship-aware world using passive RFIDs. So this project is in collaboration with Jinxian, Zijian, Suoruan, and Jason at Carnegie Mellon University. So in this paper, we ask one question: how can we design a responsive world and make the whole world, the whole physical world, interactive? We propose WiSh, a wireless ship sensing solution, which makes ordinary surfaces ship-aware using low-cost, waterproof, battery-free RFID tags, which can fundamentally change the way we interact with our daily environment today. So imagine a ship-aware toy can respond to all your touch and press. Or consider the smart carpets can correspond differently based on where and how they are depressed. At a larger scale, consider the bridges that can track the fine-grained curvature to track the structural hairs. In the WiSh world, once the surface is instrumented with RFID tags, we can sense the ship based on wireless channel observations. So as you can see, knowing the ship can enable so many applications. But how can we sense ships today? So there are two types of solutions. The most common one is to use an external visual sensor. We can install a depth camera or a LiDAR in the environment to scan the ship. The visual sensing is usually a static configuration, and the target surface needs to be in the direct line of sight. It's not practical to place the visual sensors everywhere in the world to make the world ship-aware. So the alternative solution is you can attach electronic sensors to the surface. For example, sensor tape is a dense sensor network in the form factor of a tape. So sensor tape uses IMU sensors to sense the bend and twist. However, these solutions are quite expensive and delicate. They require battery and special attentions because these sensors are not waterproof. Differently, WiSh is designed to be a mobile, ad hoc solution that supports non-line-of-sight objects. Besides, WiSh surfaces would be battery-free, durable, and low-cost. So here we present WiSh, a generic solution makes ordinary surfaces ship-aware, using low-cost, waterproof, lightweight, battery-free RFID tags. At the core of our solution is that WiSh primitive that can infer the curved ships by sensing the RFID tags on the surface. In the WiSh world, we envision a reversed RFID architecture, where the readers would be mobile and the RFID tags would be massively deployed in our daily environment. And these tags would be only activated if there is a reader nearby. For example, the WiSh toy and the carpets would be powered by the mobile reader in the user's pocket. Or a vehicle with a reader installed can sense the bridge fine-grained curvature when it drives through a WiSh bridge. So how does it work? I will start with the high-level intuition and then describe our solutions in detail. At the core of the WiSh is the fact that the RFID tags on the different strips will reflect the radio signal differently. The challenge is how can we reconstruct the curved ship based on the RFID backscatter observations? There are two types of approaches for ship sensing. So data-driven and triangulation, but none of them works for WiSh. One example of the data-driven approach is the FlexSense. FlexSense collects the ground truth ships using a camera system and then maps the sensor observations to the camera observations. However, in the radio scenario, the radio signal patterns would be largely influenced by the antenna position and the unknown reflectors in the environment. The alternative solution is triangulation, such as tagram. Tagram places multiple antennas in the environment and measure the distance from the tag to the antenna, and then use the triangulation to infer the RFID tag position. However, the multi-antenna solutions cannot be mobile. Besides, when the antenna is mobile, tracking the antenna itself would be a new problem. So the ship sensing in WiSh context is actually a special problem. On the negative side, we don't know the multi-path environment. We only have one antenna at an unknown position. And there is not enough information to compute the RFID tag positions directly. But on the positive side, we can instrument RFID tags on the surface in any way we want. The real-world surfaces are very constrained, and they are not arbitrary geometries. We designed our solution to this special problem as follows. We first proposed a ship representation to leverage the real-world ship constraint. We then developed a ship modeling technique that models the complex radial environment, such as multipass. And finally, we developed a technique to optimize the ship search process. For the simplicity, I will start with 1D curve and then describe how can we expand it to 2D surface. WiSh models the surface through sensing the RFID tags on the surface. If we know the tag position, we can construct the curve easily. But the reality is we only have one measurement per tag, and we cannot compute the 2D coordinations. That's the problem of two less equations and too many variables. The good news is that the tags are constrained to the surface, so their positions are not independent. Instead of computing the tag positions directly, we use the Bezier curve. We use a parametric Bezier curve to model the surface. Bezier curves are commonly used in the graphic softwares like Photoshop. They are very good in approximating the real-world ships. We choose cubic Bezier curve for the WiSh primitives, which is controlled by the 4 points. So since we only care about the relative ship, so we can further reduce the number of variables to represent a ship. In fact, we only need 5 unknown variables to represent as a curve primitive. So we place RFID tags evenly on the surface, and here the green circle actually represents the RFID tags. And based on the ship parameters, we can deduce the tag positions. Further, this ship representation also can model the bend and the stretch. So the second step is we want to model the ship using the radio signals. We can formulate the problem as follows. We have an antenna at an unknown position, and we have no idea about the tag positions. And what's worse, the radio environment may contain multiple unknown reflectors. So given the wireless channel observation for each individual tag, how can we infer the ship representation? Our curve modeling starts with a random ship guess. Say we guess the ship is a straight line, and this guess might be wrong. But the first is we want to know how wrong the guess is. Here is the starting point. We have a random guess and the wireless channel observations. And based on the random ship guess, we can infer the RFID tag positions. Using these tag positions and the signal observation, we can estimate the angle of arrivals. And so we have an hypothetical angle of arrival. It's hypothetical because the ship may not be right. And using the angle of arrival and the tag positions, we can reconstruct a signal, which is a hypothetical signal. And comparing the hypothetical signal with the wireless channel observations, we can compute the ship prediction residue. So if the ship prediction is perfect, the residue will be 0. And if the ship guess is bad, the residue will be much larger. And this same approach will also work for multipass environment. When there are multiple refractors, we will find multiple arrival angles. We can then use these angles to reconstruct these signals and to compute the residue. The last step is ship optimization. Now we can model an individual ship guess, but how can we find the perfect ship? We can do brute force search by traversing all the unknown variables. We actually tried. So it took 5 days to traverse all the unknown variables to find the right ship. Or we can use gradient descent to speed up the process. However, the phase itself is ambiguous. So the solution search would be in the non-convex space. We cannot use gradient descent. Instead, we use a genetic algorithm to compute the ship. The genetic algorithm borrows the idea of biological evolution, which repeatedly modifies the population using natural selection and gene evolving. The genetic algorithm can be characterized into 4 components. The first component is DNA. We use the ship parameters as the DNA. And then we randomly generate a number of ships randomly. And then we evaluate all the ships and eliminate the bad candidates. And this survival will go through the mutation and crossover and generate some new descendants. And these descendants will go through the natural selection again and generate some new descendants later. This loop will run again and again until we find a good ship fate. Here is an end-to-end demonstration of the curve ship prediction. The right side is our prototype you can see all these RFID tags on the paper prototype. And the other side is the real-time, like live ship predictions. To extend the 1D curvature to 2D surface, we use Bezier surface, which is the production of two orthogonal Bezier curves. So basically, we use the same method. And in our paper, we also address other challenges as well. We develop like surface stitching technology to model the large complex surfaces. And we also incorporate material modeling and RFID tag orientations. Due to a time limit, I'm not going to introduce them. Please check them in our paper. To understand the performance, we conduct 4 sets of evaluations. We build prototypes in different sizes, using different materials, and in different shapes. And to obtain the ground truth, we develop a camera-based tracking system. We place AR markers on the surface and compute the positions of the markers and reconstruct the surface eventually. This solution provides us sub-millimeter accuracy ground truth. And we first run a micro benchmark to understand the ship prediction accuracy. We build 3-stream prototypes with different tag spacings. And we test different shapes, concave, convex, and wave-like. And we collected more than at least 500 plus ship predictions for each configuration. And here is an example of our ship prediction. The X and Y axes are the spatial location. The orange line is the ground truth observation from the camera-based system. And the dot clouds are the individual ship predictions we have. To quantify the evaluation results, we measure the distance offset between our ship prediction and the ground truth. And this green line is the average ship prediction. As you can see, all the ship predictions with an average error of 1.6 centimeter is closely aligned with the ground truth ship. So here is the overall accuracy statistics. The 3 color bars indicate the average distance offset for 3 prototypes with different tag spacing. All these prototypes have a very good accuracy with an average error distance between 1.3 and 1.9 centimeter. And we also test how well WiSh works in the multipath environment. These 3 color bars correspond to the line of sight, multipath, and non-line of sight. The average offset is between 1.1 and 2.3 centimeter. And besides, we then also test different materials and different stress for 1D string and 2D surfaces. We bend and stretch the fabrics, and please see details in our paper. Using the WiSh primitives, we develop various applications, such as smart ship-aware bridge, 3D touchscreen, spine posture, breeze sensing, and smart carpets. The first application I'm going to introduce is ship-aware bridges. So today, 1/4 of US highway bridges are in need of serious repair. However, routine visual inspections are costly and time-consuming. WiSh can make bridges ship-aware at a very low cost. We run our experiment on a major bridge in Pittsburgh, which is a 388-meter long suspension bridge. Since deploying the sensors on the bridge requires a special license, we developed a ship sensing tape instead. We stick 50 tags on a 5-meter string with an evenly 7 centimeter tag spacing. And at the beginning, you can see a programmable robot. It will drag the tape at a constant speed. And here is the scene when we test the sensing tape on the real bridge. And during the process, WiSh continuously sense the tape curvature and associate the ship predictions with the bridge segments using the timestamp and the movement speed. So this is how the bridge looks like. And the red line highlights the area we have measured with WiSh. And when we merge all the segments, we have our ship prediction, which is well aligned with the bridge schematics. And another example use of WiSh is turning any soft object in our daily environment into an interactive surface. So we built a 3D touch screen using 35 RFID tags. And the touchscreen prototype has a mean prediction accuracy at 87%. So while WiSh is promising, it has several limitations. The first, WiSh cannot model small curvatures such as wrinkle and folds, because RFID itself is kind of large, like at 3 centimeter size. Second, our computation speed is actually cannot catch up a raw signal refresh rate, while our raw signal refresh rate is around 30 Hertz, and our algorithm currently can only process 2 frames per second. So here I conclude my presentation, which is a genetic wireless chip sensing solution that can make our surrounding environment responsive using passive RFIDs. And I'm happy to take any questions.